cis pent to ene adds upon singlet carbene to give cis product, whereas trans pent to ene adds singlet carbene to give the trans product. Triplet methylene reacts in two steps, and addition is non-stereospecific in nature, that is, reaction of either cis or trans but-2-ene with triplet methylene gives the same mixture of cis and trans 1,2-dimethyl cyclopropene. The first step in the addition reaction involves the formation of biradical. It may undergo spin inversion or a free rotation about carbon-carbon single bond before it cyclizes to give a mixture of cyclopropane derivative. Similarly, trans-2-butene also gives mixture of cis or trans 1,2-dimethylene cyclopropane. Dichloromethylene adds to alkene when treated with chloroform in presence of potassium tert butoxide. The reaction is highly stereospecific in nature, that is, a particular stereoisomer of the reactant produces a specific stereoisomers of the product. Simmons-Smith reaction. Free carbenes are not very useful for addition to double bond since these are extremely reactive and undergo many side reactions, especially insertion reactions. A better method which gives better yield of cyclopropane involves Simmons-Smith reaction. In this reaction, alkene is treated with diodomethane and a zinc-copper couple. The actual attacking species in organozinc intermediates, methylene iodide and zinc reacted to form carbene-like species called carbenoid. The carbenoid brings out the stereospecific addition of CH2 group directly to the alkene. For example, cis-2-butene reacts with CH2I2 in presence of zinc-copper couple gives cis-1,2-dimethyl cyclopropane. Similarly, trans-2-butene on reaction with CH2I2 in presence of zinc-copper couple gives trans-1,2-dimethyl cyclopropane. 7th, Thorpe-Ziegler reaction. In this reaction, a dinitrile in which nitrile groups are attached to terminal carbon atom is treated with a base such as lithium diethylamide to form a cycline iminonitrile, which is formed through intramolecular condensation. The iminonitrile on hydrolysis form a cyclic ketone, which on Clemson reduction give cycloalkane. This method is best suitable for the preparation of large ring macrocyclic compounds. The reaction proceeds through the following sequences. The first step in this reaction involves cyclization, occurs under very dilute condensation. It is referred as Ziegler high dilution technique. Cyclic ring up to 34 members can be prepared by this reaction. 8. Reduction of cyclic carbonyl compounds. A. Clemson reduction. Cyclic ketones, when reduced in presence of zinc amalgam and concentric HCl, get converted to cycloalkanes, in which keto group is reduced to methylene group. B. Wolff-Kishner reduction. Cyclic ketones, when reduced in presence of zinc amalgam and concentric HCl, get converted to cycloalkanes, in which keto group is reduced of methylene group. Wolff-Kishner reaction. Cyclic ketones when treated with hydrazine form hydrazones which when treated with KOH in glycol form cycloalkanes. Hydrogenation of aromatic hydrocarbons. Cyclohexane and its derivative can be prepared by catalytic hydrogenation of aromatic compound at high temperature and under high pressure. For example, benzene to cyclohexane, toluene to methyl cyclohexane. Physical properties of cycloalkanes. Physical properties. Number 1. Cyclopropane and cyclobutane are gases at ordinary temperature while higher member are liquids. This is because as the molecular size increases, the magnitude of van der Waals force of attraction increases. Therefore, the physical state changes from gas to liquid state. Number 2. Cycloalkanes are lighter than water. Number 3. Cycloalkanes are non-polar in nature and therefore they are insoluble in polar solvents like water but soluble in non-polar solvents like acetone, carbon tetrachloride, etc. The melting point or boiling point and densities of cycloalkanes are higher than their open chain analogues. This is because in alkanes, due to their zigzag structure, they can't properly fit into the crystal lattice, whereas in cycloalkanes, due to their compact structure, they can properly fit into the crystal lattice. Therefore, due to close packing, there are stronger intermolecular forces of attraction and hence cycloalkanes have higher melting point, boiling point or densities. Chemical properties of cycloalkanes. The cycloalkanes show similarity of two alkanes to the fact that all the carbon atoms in these compounds are sp3 hybridized, forming only carbon-carbon single bond and carbon-hydrogen single bond, sigma bond. But all the cycloalkanes are not equally stable and unreactive. Only cycloalkanes from cyclopentane onwards show a high degree of stability and are quite unreactive. As such, they are not attacked by chemical reagent like strong acids, strong alkalis, common oxidizing agent KMNO4, and powerful reducing agent LiAlH4, etc. However, like alkene, they undergo free radical substitution reaction. On the other hand, due to high angle of strain, the cyclopropane cyclobutane are more reactive than alkenes but less reactive than alkenes. Cyclopropane and cyclobutane rings are not very stable and have a tendency to undergo ring cleavage, forming addition products. Thus, they resemble alkenes in undergoing addition reaction. However, they are much less reactive than alkenes. Some of the important chemical reactions of cycloalkanes are: number 1. Free radical substitution reaction. Cycloalkanes undergo free radical substitution reaction with halogens at 525 to 575 Kelvin in the dark or at room temperature in presence of light. Number 2. Addition reaction. Like alkenes, cyclopropane undergo addition reaction. However, unlike alkenes, cyclopropane does not add ozone and also does not undergo hydroxylation with aqueous KMNO4 solution. Cyclobutane, on the other hand, is less reactive than cyclopropane and hence does not undergo addition reaction under ordinary condition. However, on hydrogenation at higher temperature, it gives N-butane. From the above discussion, it is evident that cyclopropane is the most reactive of all the cycloalkanes and undergo many addition reactions through ring cleavage. Cyclobutane is less reactive than cyclopropane and undergo only addition of hydrogen, while rest of the cycloalkanes are unreactive and do not form addition product. Instead, like alkanes, they yield substitution products. Relative stabilities of cycloalkanes. Bayer's strain theory. The relative stability of different cycloalkane can be explained on the basis of their angle of strain, which are introduced by Beers. He explains the difference in the reactivities of different cycloalkanes on the basis of his Beer strain theory put forward in 1835. The main points of the theory are: number 1. In cycloalkanes, each carbon atom is sp3 hybrid, therefore it should be bonded to 4 other carbon atoms, and angle between any pair of adjacent bonds should be 109.5 degree. Number 2. Cycloalkanes, due to their cyclic structure, are planar in nature. The bond angle between adjacent carbon atoms in the ring are no longer equal to normal tetrahedral angle, that is 109.5 degree. The deviation of the angle varies with the size of ring. Number 3. Any deviation or distortion from the normal tetrahedral angle causes a strain in the ring, which is known as the angle of strain. Angle of strain is equals to half into 109.5 degree minus bond angle in the planar ring. Number 4. The greater the deviation from the normal tetrahedral angle during the formation of ring, greater will be angle of strain, and hence greater the reactivity of cycloalkane. The age of formation of cycloalkane is directly proportional related to stability of ring. Stability of ring is inversely proportional to angle of strain. 6. The more reactivity stability of cycloalkane, the more easily it is formed. Evidences in favor of Bayer's strain theory. The following fact favors Bayer's strain theory. Reactivity of double bond in alkenes. According to Bayer's strain theory, double bond is treated as two-membered ring structure having bond angle 0 degree. So the angle of strain in alkenes is, as alkenes have very high angle of strain, hence it proves the unstability and reactivity of alkenes. Number 2. Reactivity of cyclopropane and cyclobutane. Both cyclopropane and cyclobutane have A. High value of angle of strain, B. High value of heat of combustion. So both cyclopropane and cyclobutane are unstable and reactive. Limitations of Bayer's strain theory. The Bayer's strain theory can't explain the following facts. Number 1. Stability of cyclohexane and higher membered ring. According to Bayer's strain theory, cyclohexane and higher membered ring have high angle of strain, so they should be unstable as per Bayer's strain theory, but cyclohexane and high membered ring are stable. Hence, Bayer's strain theory can't explain the stability of cyclohexane and higher membered rings. 2. Occurrence of dehydrohalogenation of alkyl halide and dehydration of alcohol. As per both, dehydrohalogenation of alkyl halide and dehydration of alcohol gives alkenes. Further, as per Bayer's strain theory, the double is treated as the two-numbered ring structure having bond angle 0 degree, so the angle of strain in alkenes is A. As alkenes have very high angle of strain, so alkenes should be unstable. Hence, Bayer's strain theory can't explain the occurrence of both dehydrohalogenation of alkyl halide and dehydration of alcohol into alkenes. Morse theory of strainless strain. The main point of this theory are: number 1. All atoms in cyclopentane and lower member ring are present in the same plane. Number 2. All atoms in cyclohexane and higher membered ring are not present in same plane, that is, they have puckered structure, non-planar structure with normal tetrahedral angle, so they have zero angle of strain. Hence, cyclohexane and high membered ring are stable. As cyclohexane and high membered ring have zero angle of strain due to their non-polar structure with normal tetrahedral angle, so Morse theory is also called theory of strainless strain. Once bigger rings are formed, they are quite stable due to absence of angle of strain. The bigger rings have no angle of strain, but they are difficult to form to more distance in between the two ends of the chain. Structure of cyclopropane. In cyclopropane, the hybridization of each carbon is sp3 and the expected bond angle should be 109 degree 28 minute, but the internal bond angle is of 60 degrees, so there is considerable deviation from the tetrahedral angle of 109 degree 28 minute, and the occurs large bond pair repulsion. To minimize the bond pair repulsion, electron density is somewhat shifted outwards on one side of the internuclear axis. So in cyclopropane, the distribution of electron density is not uniform on either side of internuclear axis. The bond is bent outward by some angle called bent angle and giving the appearance of bananas. So the carbon-carbon bond is cyclopropane is called bent or banana bond. The bent angle theta is determined by drawing tangent through the old position of bond and new position of CC bond in cyclopropane. Thank you.